We're going to learn today about how recursion and the calculator or other technology can be used to solve problems. Today we're looking at the swimming pool problem. So the first part of the swimming pool problem goes like this. If it's never refreshed, the water in a swimming pool becomes polluted after some time. Urea that comes into the water via body secretions is one of the substances that pollute swimming pools. Now some of you are thinking, urea, oh, that's like urine peeing in the pool. Well, that's part of it, but urea is a more general substance that could be found in sweat, other things that come out of your body besides just peeing in the pool. Assuming that there are an average of 1,000 swimmers per day, the amount of urea in the pool increases by 500 grams per day. When there are 4,000 grams of urea in the water, the swimming pool will be closed to the public because the water has to be cleaned. Okay, 500 grams per day, 4,000 total. That means how many days until the pool has to be closed? Yes, my brilliant students, 8 days of use and the pool will have to be closed. So let's see what the solution here is. The cleaning equipment in the pool can remove 20% of the amount of urea present in one day. So the first day, 800 grams of urea can be removed. That's 20% of 4,000. The second day, 20% of the remaining amount of urea will be removed, and so on. The pool can be reopened when the amount of urea in the pool drops below 2,000 grams. How many days will the pool have to be closed for cleaning? So let's look at the sequence that we form by investigating this problem. So there's our starting amount of urea, 4,000 grams. Day 1, 20% of 4,000 or 800 is removed. So 3,200 grams remain. Day 2, 20% of the 3,200 is removed. That's 640. So 2,560 grams remain. Now some of you at this point may be realizing that there is a more efficient way to do this. Since I'm interested in how much urea remains after cleaning, instead of multiplying by 0.2 and subtracting, I could do a more direct calculation. If 20% of the urea is removed, then 80% must remain. So multiply the previous day's total by 0.8 instead of multiplying by 0.2 and subtracting. This is called recursion. And actually what we did before was actually recursion as well. Recursion can be done easily using technology. So anytime we're referring back to the previous term, it's called recursion. Okay, so let's look at what's going on here. And actually I want to look at this part before I look at the calculator use. So let me slide this over here. And go down. Okay. So day 1 is 0.8 times 4,000. Day 2, 0.8 times 3,200. Day 3, 0.8 times 2,560, etc. If we do this on the calculator, okay, and actually I want to show you kind of live on a calculator here. But we can see here that after 4 days of this, we've dropped below 2,000, so the pool can reopen. Okay, so just to show you here, we start out as, here's our 4,000, push enter, and then we say the answer. So if you just push times here, it picks up the answer, times 0.8, enter, 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 enter. So we can see 4 days of cleaning and we're ready to open. The trouble is we're starting out now with 1.638. So how many days until we close again? Well, we have to add 500. So plus 500. 1, 2, 3, 4, 5. Okay, we have to close again. All right. So now we do the 0.8. So times 0.8. 1, 2, 3, 4 more days till we have to get to open again. So this is clearly a foolish way to run a swimming pool, is to open for 8 days, open for 8 days, close for 4 days, open for 5 days, and then we have to close again to clean, and that's silly. Okay, foolish way to run a swimming pool here. So what's a better solution? All right. A better method of keeping the amount of urea under control is to let the people swim during the day and refresh the water during the night. Brilliant! Starting with a clean pool, no urea in the water, swimmers will add 500 grams of urea to the water every day. Each night, 10% of the urea in the water will be removed. So remember, since we're removing 10%, then 90% remains. Will this process allow them to keep the urea content of the pool at an acceptable level? If not, give a specific suggestion for a change in their procedure if needed. So once again, let's investigate. Day 1, 500 grams of urea is added to the pool. Night 1, 10% is removed, so 90% remains. So we have 450 to start out the next day. The next day, 500 is added for a total of 950. Night 2, we remove 10% of the 950, so 90% of the 950 remains. That's 855. And you're thinking, uh-oh, we still have the same problem. It keeps going up. But let's investigate a little further. Day 3, we add 500 to what remains of the 855, and then take 90% of the 855, and then we have 121940. And we're getting bigger, but what you should notice is the amount of increase has decreased. So 450 plus 405 gives me 855, but if I added 405 again, that would be 1260, and it's only 1219. So it didn't increase by the same amount. So maybe if this trend goes down, we'll notice that this might work after all. Okay, so let's look at what we did here. Every time we start by adding the 500. We multiply, so we take the previous day 1's total by 0.9, and then we add 500 again, and then that times 0.9, and then add 500 again, and then that times 0.9. So each time we're adding 500 to the previous total and then multiplying it by 0.9. So we can look at this kind of symbolically here. We can see it on the calculator at the same time. Okay, so our starting amount is 0. Then we took previous amount plus 500 times 0.9. Then we get 450. 450 plus 500 times 0.9. So in other words, we took a sub 0 plus 500 times 0.9 to get a sub 1. A sub 1 plus 500 times 0.9 to get a sub 2. Then we're going to take a sub 2 plus 500 times 0.9 to get a sub 3. So in general, we're taking to get a sub n, we're taking a sub n minus 1 plus 500 times 0.9. Now on your calculator, you don't use a sub 1. What you use is the answer. Okay, and I'm actually showing this 2 different places. Answer plus 500 times 0.9. So here's I did the first one just kind of by hand, 500 times 0.9, then answer plus 500 times 0.9, and then once you do that, you are just iterating. And I think it looks like I sort of started over. Oh, I was showing what I did here, and then I showed what it looked like actually when you do it on the calculator. So let's go to the calculator and do this. I'm going to clear off what I've done here, and let's start out with our actual amount 0. That's actually our starting amount of urea. And then we're going to take the answer. So if you do control, then this negative sign, you get answer plus 500 times 0.9. Okay, there's the 450. Then if I hit enter again, see it takes 450 times 500 times 0.9. And then, so those are our first few values. So let's see what happens in the long run. It's still going up, and it's gone over 4,000. But notice how the amount of increase has really gotten small. Okay, so now it's only increasing by less than 10 each time. So I'm going to just keep pushing enter for a little while and I can do this for a while. Oh my gosh, it looks like it's leveled off. It's not increased at all. So it looks like if we kept going with this process, eventually we would have a sustainable level at 4,500 grams of urea, which is still higher than we want, but we do see that this is a sustainable process. So what we're going to have to do, and I'll kind of take this off. Okay, so this is what we ended up with. We ended up, after a long time, we get 450 and it 4,500. So what would we have to do to make a sustainable level at 4,000 or below? Well, it would be helpful if we could take out a little bit higher percentage in the evenings. Okay, so, or else the other alternative would be allow fewer people in the pool, so this 500 amount is not as high. But if we want to keep 1,000 people in the pool, we're just going to have to remove more at night. So maybe buy another cleaning machine or something. So here's a couple of examples. If we'd made that 0.8 instead of 0.9, we could have a sustainable level at 2,000, which would keep the pool a lot cleaner. If we felt like that was too cost prohibitive, we could use 0.875 and get it sustainable at 3,500. So this is a really good way to explore and do examples using iteration, and it doesn't take very long to do on your calculator. You just have to come up with the recursive formula. The way you come up with the recursive formula is to do a few examples by hand and see what you're doing with the process, and then do it on the calculator. Now something that you might, let me go back to the previous example. You don't actually have to deal with the 80% instead of the 20%. So here we are doing each time previous answer minus 20% of previous answer equals new answer. New answer minus 20% of new answer, or previous answer minus 20% of previous answer equals new answer. So on the calculator, you can actually do it that way if you want to. So if we go to the calculator again, and let me clear this one off. So let's say we went back to the first problem, 4,000. And I wanted to say, okay, now I want to do 4,000, so that is the answer minus 0.2 times the answer. So I want to subtract 20% of 4,000 from 4,000. I'm going to subtract 20% of 3,200 from 3,200. And so I could also do it that way and get the same results. So if that makes more sense to you to separate it like that, you can also use recursion on your calculator to do it that way. Okay, so hopefully that was helpful to you. When you do the problems in your packet, there'll be a similar kind of thought process to this.